Hello everyone, so this will be the second part of the film holders recorded lecture. So from the first part, we have already talked about the parts of the intensifying screens. And we already know that in an intensifying screen, there is what we call a phosphor layer, which is the active layer of our intensifying screen. It is where the light is emitted by the phosphor when struck by an X-ray energy. So for our phosphor, we have two types or two materials that was used, and that is the calcium tungstate and rare earth. So our calcium tungstate is the active substance of most phosphors before about 1980. So these are crystalline calcium tungstate embedded on a polymer matrix. This was developed by Thomas Edison within 1 year of Roentgen's discovery of X-rays, because the phosphor that was used by Roentgen upon the discovery was the barium platinocyanide. Again, the phosphor that was used by Roentgen upon discovery of X-ray was barium platinocyanide. But that was never successfully applied to diagnostic radiology. So aside from calcium tungstate that was used as a phosphorus, we also used the zinc sulfide. Okay, we have also used the zinc sulfide, and that is used for a low KVP technique that provides a high resolution image quality. Again, zinc sulfide was also used as a material of phosphor, and it uses a low KVP technique for a higher resolution of image quality. So using zinc sulfide lowers down the quantum motel or decreases the quantum motel. Therefore, if the zinc sulfide uses a low KVP technique to produce a high quality of image, we have to increase MAS for the compensation. Aside from zinc sulfide, we also used the barium lead sulfate. The barium lead sulfate is used as a phosphor by having a high KVP technique that is used to decrease the patient dose. So using barium lead sulfate as a material of phosphor increases the spatial resolution and increases fog that contributes to an added density on the radiograph. Therefore, to compensate the increase in density, we have to lower down the MAS. So before rare earth crystals being the phosphor or being the material used as a phosphor, we have calcium tungstate, zinc sulfide, and barium lead sulfate. Again, zinc sulfide is used for a low KVP technique to produce a high quality image, but therefore if the KVP decreases, we have to compensate it by increasing an MAS. So the use of zinc sulfide as a phosphor material increases patient dose, unlike barium lead sulfate, which is used to decrease the patient dose by giving the KVP a higher technique. Therefore, to compensate the fog that was produced by a higher KVP, we have to decrease the MAS. Okay? So the rare earth screens are faster than calcium tungstate. So the use of rare earth screens results in lower patient dose and less thermal stress on the X-ray tube and reduced shielding for X-ray beams. So for our rare earth, we have gadolinium, lanthanum, and yttrium. So these three rare earth crystals have a higher atomic number or higher atomic number where it absorbs most of the X-rays. As the crystals absorb most of the X-rays, it will emit the light. Next, let's talk about the properties that a phosphor should have. So first is the detective quantum efficiency, where the phosphors should have a higher atomic number so that X-ray absorption is high. And the crystal or the material that was used as a phosphor, which have a higher detective quantum efficiency, is the rare earth crystals. As I've mentioned, the lanthanum, gadolinium, and yttrium have a higher atomic number compared to the calcium tungstate. Okay? So next is the conversion efficiency. So it is where the phosphor should emit a large amount of light per X-ray absorption. Next is spectral matching, which the light emitted must be of proper wavelength to match the sensitivity of the X-ray film. And then the phosphor afterglow should be minimal. When we say afterglow, it is where once the phosphor was trapped by the X-ray energy, there should be no afterglow. It should not emit light after the exposure. Because once that it continuously emits light even after the exposure, it could add some density on the image. It could deteriorate the image quality. Last is that the phosphor should not be affected by heat, humidity, or other environmental conditions. Okay, so we have mentioned that the phosphor should not emit light after exposure, or the phosphor afterglow should be minimal, because we know that phosphor emits light and therefore it is a luminescent material. When we say luminescence, any material that emits light in response to some outside stimulation is called luminescent material or the phosphor. So luminescence is the emitted visible light. We have two types of luminescence. First is fluorescence, where visible light is emitted only while the phosphor is stimulated. Next is phosphorescence, or yung tinatawag natin na afterglow. It is where the phosphor continues to emit light even after stimulation. And I've said earlier that the properties of the phosphor should have a minimal afterglow. Okay. So now let's proceed to the primary characteristics of intensifying screen. First is the screen speed. It is where the relative number that describes how efficiently X-rays are converted into light. So ito yung tinatawag nating mga slow speed or par speed, yung mga naririnig natin na tawag sa screen speed, or especially the high speed screens. So we have here the intensification factor, and is defined as the ratio of the exposure required to produce the same optical density with a screen to the procedure, or to the exposure required to produce an optical density without a screen, and it measures the speed of the screen. So here is the formula for intensification factor. Okay, so intensification factor is equal to the exposure required required without screen and the exposure required with screen. Again, intensification factor determines or measures the screen speed. Okay? Next is the image noise. So image noise appear as a speckled background, and it occurs most often when fast screens and high KVP technique are used. So it also reduces image contrast. So si image noise, yun yung parang salt and pepper na nakikita natin on the radiograph. Next is spatial resolution, refers to how small an image can be imaged or can be seen, can be viewed. So to determine the spatial resolution, a line pair test pattern consists of lead lines separated by interspaces of equal size. So yun yung pang test to check the spatial resolution. Okay, going back to the screen speed, I will show you or I will give you the values of different types of screen speed. Okay, first we have a slow or detail screen. For slow or detail screen, its intensification factor is 50 to 80. While the par speed screens measured at about 100. And par speed screens is the basis for the comparison of all other screens. Par speed screens usually is made up of calcium tungstate phosphors. When we say par speed screens, it is also called the standard, the medium, or the par screens. Last is the high speed screens. High speed screens measures at about 1,000 to 100. And high speed screens uses rare earth crystals as the phosphor. Okay, again, these are the values of the screen speed. We have slow or detail screen that measures at about 50 to 80, and then we have par speed, which is the basis for comparison of all other screens, the values of 100, and par speed screen uses a calcium tungstate phosphors. Last is the high speed rare earth screens that measures at about 1,200, and again, this uses rare earth crystals as a phosphor. Okay, so actually intensifying screens have properties where the RadTech cannot control. First is the phosphor composition, in where the rare earth efficiently converts X-ray into visible light. The phosphor composition, only the manufacturer can determine it, whether it will be composed of calcium tungstate or rare earth crystals. But again, rare earth efficiently converts X-ray into visible light. Next is phosphor thickness. Again, phosphor composition and phosphor thickness are always based on the manufacturer. So when phosphor thickness, the thicker the phosphor layer, it will have a higher detective quantum efficiency. Thicker phosphor layer, higher detective quantum efficiency. So high-speed screens have thick phosphor layer, and then fine detailed have thin phosphor layer. Next is the reflective layer. Reflective layer increases screen speed but also increases image blur. Next is dye. The light absorbing dye that is added to control the spread of light improves spatial resolution but will reduce speed. Next is crystal size. The larger individual phosphor size produces more light. Again, larger crystal size produces more light. Crystals of fine detail screens are approximately half of high-speed crystals. And last is concentration of phosphor crystal. Higher concentration, higher screen speed. Again, these are the properties of the intensifying screen that are not controlled by RadTech. But these properties are based on the manufacturer of the screens. If there are properties that cannot be controlled by the RadTech, it also have properties that are controlled by the RadTech. First is the radiation quality. Okay, so radiation quality, as X-ray tube potential increases, the intensification factor also increases. Again, as X-ray tube potential increases, the intensification factor also increases. Now, the question is, what is the X-ray tube potential? What controls the X-ray tube potential? And that is the KVP. KVP is one of the technical factors that can be adjusted by RadTech depending on every procedure. So screens have higher effective atomic numbers than films. Therefore, although in true absorption in the screen, it decreases with increasing KVP. So relative absorption compared with that in film increases. Okay? So again, as X-ray tube potential increases, the intensification factor also increases. Next is image processing. So the excessive developing time for screen film results in lowering of the intensification factor because the emulsion nearest to the base contains no latent image, yet it can be reduced to silver if the developer is allowed sufficient time to penetrate the emulsion to the depth. So again, image processing in where the excessive developing time will lower the intensification factor. Ito yung tinatawag natin na nasusunog yung plaka kapag napababad ng sobra sa developer. Last is the temperature. So for temperature, radiographic intensifying screens emits more light per X-ray interaction at low temperatures than at high temperatures. Therefore, intensification factor is lower at high temperature. Okay, so those are the properties that can be controlled by the RadTech, and those are the properties of the intensifying screen. If you have questions for this topic, you may leave you may leave a message on my messenger or even on our group chat. Okay, so thank you everyone.